Buenos días a todos ustedes. Espero que me puedan ver, que no vean solamente mi fotografía, aunque esté yo muy bien acompañada en ella. Estimado público, muchas gracias por asistir a esta sesión especial del Congreso Nacional de Física, en la que tendremos el placer y el honor de escuchar una conferencia dictada por el profesor David Gross, quien entre otras cosas pues, recibió el Premio Nobel de Física en 2004 por descubrir junto con otros dos colegas lo que se llama la libertad asintótica, que es un término que más allá de su significado físico concreto, como que es sumamente sugestivo. Nos va a hablar hoy de las fronteras de la física teórica y será presentado por Eugenio Méndez del CICESE, de manera que a mí solamente me toca agradecer naturalmente al profesor Gross en primer lugar su buena disposición no solamente a dar esta conferencia, sino a trasladarse a Tijuana para poder dictarla. Muchísimas gracias, profesor Gross. Thank you very, very much for joining us in this, the 64th National Congress of Physics, organized by the Mexican Physical Society. We are deeply honored and pleased to have you as a very special part of this conference. Naturalmente la conferencia pues la va a dar en inglés el profesor Gross, así que invito a todos ustedes a aguzar sus oídos. No tenemos traducción simultánea, pero el profesor Gross sabe que pues no somos tan versados en el idioma inglés, de manera que seguramente que va a dictar su conferencia tomando esto en cuenta. Los dejo entonces en buenas manos. Eugenio, te paso el micrófono.
Buenos días a todos. Good morning to everybody. On behalf of the Mexican Physical Society and the physics community of Baja California, it is my great pleasure to welcome here today Professor David Gross of the University of California, Santa Barbara. For the benefit of those who are not familiar, oops, I think I pressed something here. For the benefit of those who are not familiar with his work, I will read a few words about him, and for this I will switch to Spanish. Profesor David Gross es el Chancellor's Chair Professor de Física Teórica de la Universidad de California en Santa Bárbara. Debo decir que este título de Chancellor's Chair Professor es una distinción universitaria reservada para personas que, además de haber alcanzado méritos académicos extraordinarios, se considera altamente probable que continúen produciendo trabajo académico sobresaliente. Es decir, no es una cuestión meramente para alguien retirado, es alguien que se espera que está produciendo cosas muy interesantes, muy importantes. Él ha sido director del reconocido Instituto Calvi de Física Teórica de la misma universidad, en donde continúa trabajando, y antes fue profesor Thomas Jones de Física Matemática de la Universidad de Princeton, que otra vez es una cátedra distinguida de la universidad. El profesor Gross recibió su doctorado de la Universidad de California en Berkeley y ha sido una figura central en el desarrollo de la física de partículas y de la teoría de cuerdas. Su descubrimiento, en colaboración con su alumno Frank Wilczek, de la libertad asintótica, que es la característica principal de las teorías de norma no abelianas, lo condujo a formular la cromodinámica cuántica o teoría de interacción nuclear fuerte. La libertad asintótica es el fenómeno por el que a distancias cortas la fuerza nuclear se debilita, lo que explica por qué los experimentos a muy altas energías pueden ser interpretados en términos de partículas nucleares formadas por quarks que no interactúan. La otra cara de la libertad asintótica es que la fuerza entre quarks aumenta conforme uno trata de separarlos, lo que explica por qué el núcleo nunca podrá romperse en los quarks que lo constituyen. La cromodinámica cuántica completó el modelo estándar que detalla las tres fuerzas básicas de la física de partículas: la fuerza electromagnética, la fuerza nuclear fuerte y la fuerza nuclear débil. Por este descubrimiento, el profesor Gross fue galardonado en 2004 con el Premio Nobel en Física, junto con Frank Wilczek y David Politzer. El profesor Gross también ha hecho aportaciones fundamentales a la teoría de supercuerdas, una aventura prometedora que trae la gravedad al contexto cuántico. Con sus colaboradores propuso la teoría de cuerdas heteróticas, la candidata principal para lograr una teoría unificada de todas las fuerzas de la naturaleza. Los premios que ha recibido incluyen los premios Sakurai, MacArthur, Harvey y el de Física de Partículas de la Sociedad Europea de Física. También la medalla de Irak, la gran medalla de oro de la Academia de Ciencias de Francia y, por supuesto, el Premio Nobel de Física en 2004. Ha recibido títulos honoríficos de universidades de Estados Unidos, Gran Bretaña, Francia, Israel, Argentina, Brasil, Bélgica, China, Filipinas y Camboya. Es miembro de varias sociedades científicas, entre las que destacan la Academia Nacional de Ciencias de Estados Unidos, la Academia Americana de Artes, de Ciencias y la TWAS, the World Academy of Sciences, además de las academias de ciencias de la India, Rusia y China. Okay, I'm back to English now. As you can see, we are very fortunate to have him as part of this meeting. And today, Professor Gross will share his thoughts, his views on the frontiers of fundamental physics. Please welcome Professor David Gross.
Thank you very much for that kind invitation. Buenos dias. It's really great to be here in Tijuana. You know, I don't live that far from Tijuana, but unfortunately, very unfortunately, the real distance, not the physical distance, is unfortunately too great between our two countries. And I also feel between our communities of scientists. But I'm delighted to be here in TJ for the first time, and I've especially enjoyed meeting the guy who invited me, and I guess was responsible for much of this, Miguel, and the whole Quark group, which are doing very impressive activities in science communication, which is so important. I really am very impressed by what they are doing and hope to continue to interact with them. Let's see. So I am going to give a very broad talk today. Hopefully there'll be some time for questions on, well, once we get this going. Okay, that's okay. No, here we are. It's working. So I'm going to talk about the frontiers of fundamental physics, and which is a big subject, and I'll just touch on a few areas. But in thinking about the current state of research in physics, it's always instructive to think back on what we have learned. And I can still remember 50, even 60 years ago, what we knew about the physical world. And it's quite amazing how much we have learned in the last 50 years, even more so in just the last 100 years, a very short time in human history. In my field, in the last 50 years, we have discovered and understood the basic building blocks of matter. What is stuff made out of? and how these elementary constituents of matter interact among themselves, how they form bigger objects. In the field of astronomy, which the first science, we have in the last 50 years mapped more or less the entire universe in some detail, and in great detail reconstructed and understood the history of the universe from the beginning, which is still confusing, till now. And coming back to ordinary matter, with the advent of quantum mechanics just about 100 years ago, we have understood how atoms and molecules work and are now able to truly understand and control atomic matter in many of its complicated phases or forms and probe matter and control it down to the nanometer scale of atoms themselves. But I always like to say that the most important product of knowledge is ignorance. And of course, I don't mean the kind of ignorance that leads to vaccine resistance or bigotry or racism, but rather new questions. So new questions that are only possible to pose, to ask, when you have the sufficient knowledge to ask them. And those are questions that drive science. They are the motivation for continuing to do scientific research. Questions that can be approached by science, which means by observation, by experiment, and by theory. So the way I picture it, we live in a sea of ignorance. Most of the structure of the universe and the laws of the universe, we probably do not yet know. We have learned a lot, and on the frontiers of our knowledge, we have many, many new questions. And in fact, the more we know, the more we learn about our ignorance. And that's what drives science forward. So I'm going to, in this talk, try to briefly touch on a few areas of ignorance, which define indeed the frontiers of science, the frontiers of physics. And I don't have time to talk of all the frontiers of physics. There are so many wonderful questions, wonderful areas. I'm going to start at the biggest scale, that of cosmology, the structure of the universe, and then go down to black holes, which have become so popular and interesting as we can now observe them throughout the universe, and for theorists like me, explore them as theoretical experiments to understand quantum gravity. And then we'll go down even farther to the scale of ordinary quantum matter. That was the atomic scale of 10 to the minus 9 meters, nanometers, where 100 years of pushing the frontiers of quantum mechanics, we now are beginning to truly understand in great detail the nature of quantum matter, its different phases, and to construct new forms of matter, which might be very useful, for example, for quantum computing. Then we'll go even deeper to the area in which I now work, where we are being pushed to think about, unfortunately not to probe directly, what might be the fundamental scale of physics, the so-called Planck scale, where quantum gravity becomes important, and we strive to unify all the forces of nature. This is a rapid tour through 5 different areas of defining the frontiers of physics. So let's start with the universe, and let's start at the beginning. Well, as I remarked, in the last 100 years, especially the last 50 years, we have learned so much about the universe. From the beginning, early on, a period of rapid expansion called inflation, to the first picture of what the universe looked like. We can see light coming from a hot gas that existed a few 100,000 years after the beginning, whatever that means. And it's been traveling towards us for over 13 billion years. And we understand and have measured the properties of this almost homogeneous gas with slight inhomogeneities or clumps of matter that eventually clump together. We understand, it seems, some astronomers, astrophysicists, cosmologists can explain how that almost homogeneous gas clumps under gravity to form these strands of matter, and then galaxies and stars and planets and us. And we know the age of the universe since early on, the beginning, very precisely, 13.7 billion years. And this standard model of cosmology, astrophysics, is extraordinarily successful in explaining how structure, how galaxies evolved, what the universe looks like today. It's quite a remarkable achievement of mankind over the last 100 years. But of course, even this successful explanation raises new questions that perhaps are now ripe for answering, very deep questions. We have measured, observed that the universe contains a kind of back energy in empty space, vacuum energy and negative pressure that causes the universe to, again, undergo accelerated expansion. And we don't know how long that will go on, forever, and if so, that leads to very interesting predictions as to the fate of the universe. But most importantly, we have no idea what happens at the very beginning, so-called Big Bang, or how did the universe begin? This is a very, perhaps the most difficult question we face, and it's not clear that we can answer it, but it has now become not just a question for religion or philosophy, but for science. We try in a variety of ways to probe early on with all sorts of signals, and hopefully not too far in the future, gravitational waves that were produced very early on, very close to the beginning, whatever that means. And physics, in my opinion, is faced with a challenge. If we want to understand the universe, we should have an explanation of the beginning, the so-called initial condition. You know, in physics, we have initial conditions and we have equations that make predictions about the future. But what sets the initial condition? That's not a question that physics has had to deal with until now. It's not obvious that physics can answer this question, but we certainly are going to try, and we are. The beginning of space-time, the beginning of the universe is very hard to imagine how you would understand that. How can you understand time beginning? What happened before time began? Or maybe the universe didn't just begin, it collapsed and then expanded. It's cyclic. There are all sorts of ideas, none of them very good or quantitative or consistent. So this is, I think, one of the biggest challenges for fundamental physics. And unfortunately, I'm not sure it'll be answered in my lifetime, probably not. But I do believe there will be an answer. We're probably not asking the question correctly as. But then in our model, our theory of the universe, we have a, I think it's a cable issue. Anyway, in our, well, they get it back on. In our theory of the universe, we have to make the theory, the model of cosmology work, you have to know how much matter there is in the universe. A lot of the matter we can see in stars, planets. But it has been discovered that there's a lot of matter out there, so-called dark matter, that is invisible, but it's indirectly visible because of the gravitational effect it has on other stars. It's called dark matter, and most of the matter in the universe appears to be in the form of this dark matter. And then, as I remarked earlier, astronomers have also measured carefully how the universe is expanding and discovered that its expansion is accelerating. And that can be attributed, most likely, to what Einstein called the cosmological constant, which is a kind of energy pressure that exists in the vacuum. Even though there's nothing there, the vacuum behaves like a gas, if you want, except that in addition to energy, this gas has negative pressure. Very strange, but a consequence of Einstein's theory of relativity, and that's what causes this accelerated expansion. And most of the energy in the universe, 75%, is this so-called dark energy. And whether we really understand that or not is not so clear. It seems to be consistent with that explanation, but dark energy is not very accessible, and its only observable feature is that it causes this accelerated expansion. So let's see. So let me just get a clue as to where I am while they try to fix it. So anyway, I'm just trying to figure out where we go from here. Dark energy, dark matter. So the beginning of the universe is unclear. So is the end. If dark energy is really the Einstein cosmological constant, the universe continues to expand in an accelerated fashion. And different regions of the universe move away from each other, eventually faster than the speed of light. So if we take our current model seriously and try to predict not the beginning, which is hard, but the end of the universe, it's a pretty weird place where every galaxy, perhaps every atom, is all on its own, expanding away from every other part of the universe and not able to communicate because the expansion exceeds the velocity of light. So indeed, here we are. Will the universe expand forever? What is our understanding, not just of the beginning, but the end of the universe? Okay, let's now go to something which has been very popular in the last few years, black holes, because unlike what Einstein thought, that they were nonsense, you couldn't have such things, it was crazy, we now understand that they exist everywhere in the universe. Every galaxy has a black hole at its center. We have a black hole at the center of our galaxy. Last year's Nobel Prize was given partly for astronomers who carefully measured the orbits of stars around the black hole in the center of our galaxy, which weighs 1 million solar masses, and we can't see directly because it's a black hole. A region of space which contains so much energy that space-time is curved and light falls back from inside the black hole and never gets out. We believe that black holes are the centers of violent events in the universe, gamma ray bursts, and finally, a few years ago, they were observed in a search for waves of gravity, waves of fluctuating space-time. And those waves are produced when I wave my hand. I produce gravity waves, but it takes the merger of two black holes or two neutron stars to create such a violent tsunami that we can measure it in these interferometers that LIGO consists of, that are able to detect a displacement of space by something like 1 part in 1,000 of the size of the nucleus. Unbelievable experiment. And that experiment detected what is interpreted, believed to be, an event that occurred a few billion years ago, far off in the universe, and produced gravitational waves that almost without any effect oscillated through the universe and hit the LIGO detector in 2015. And since then, there have been many other observations of black hole mergers and most dramatically neutron stars, which are very dense stars that have collapsed, not to form a black hole, but a form of neutron matter. The atoms are stripped away from their electrons and they're very dense neutron stars. When they collide, they also produce gravitational waves, but they also produce ordinary light waves and radio waves. And so in 2017, LIGO discovered a gravitational wave signature, alerted within seconds all the astronomical community around the world. And they looked in that region that LIGO reported and discovered an event that they could see in ordinary visible light, X-ray light, ultraviolet, infrared, and radio waves. So this was a marvelous event, and one which has taught astronomers a lot about, for example, how heavy elements in the universe, gold, platinum, lead, uranium, are produced in, it seems, often good amount of that is produced in these neutron star mergers. Okay, The frontiers of astronomy and cosmology are immense. We have incredible tools now, including gravitational wave astronomy, to probe some of these questions about the origin of the universe and its evolution. Now let's go down to the atomic scale. So now we're at the scale of nanometers, angstroms, where there has been unbelievable progress over the last 100 years. It really was quantum mechanics that started it all off, providing a theory, very strange theory at the time. Still, some people are puzzled by quantum mechanics, which is so different from classical mechanics, but enormously successful in explaining how the structure of atoms, molecules, collections of atoms, and ordinary materials, which are made out of 10 to the 23 or more atoms. What is new in the last decade or two is that we can control and manipulate and understand matter at its atomic scale with increasing precision. And we can create new forms of matter. New forms of matter, collections of atoms that aren't ordinarily present in nature around us. Theorists, like myself, also create new forms of matter on paper and with paper and pencil. And sometimes experimentalists are able to reproduce those in the laboratory, like graphene, and these new forms of matter have new properties that are enormously valuable. And we're just beginning to scratch, I think, the technological applications of our ability to create new forms of matter and understand new phases of matter. One of the biggest pushers in this field is the desire to create quantum computing. Quantum computers to deal with a problem that the computing industry is now finding. They've had Moore's law, the doubling of the power of computers every few years. It's amazing. But we're getting now down to the atomic scale, and it's not clear that one can continue this. And quantum computing offers new hope, because ordinary computers are based on bits of information, 0, 1, or in physics we might say spin up, spin down, and we put these bits together and along a tape, and we manipulate them, and that's pretty powerful for more and more of modern technology. But quantum bits are not just these classical bits. A particle with spin isn't just spin up or spin down. In quantum mechanics, it can be a superposition of spin up and spin down as measured in some particular direction. So the simplest qubit compared to a classical bit is much more complicated and richer than a classical bit, which is just either up, down, 0, 1. A quantum bit can be essentially thought of as a vector in 3 dimensions, a lot of different configurations. And when you manipulate quantum bits, the computational power, it appears, grows exponentially. In some cases, it has been shown that one can do things with quantum computers that are literally impossible ever to imagine doing with a classical computer, because it would take too long, or require a computer bigger than the size of the universe. This has pushed the study of ordinary matter, quantum matter, enormously, both theoretically and experimentally. And in my opinion, there's no doubt that quantum computers will be built. The only question is always when. The order of 20 plus or minus 10 years, I would think. Maybe 25 plus or minus. It's hard to, it's not easy, but there's an enormous investment in it. And it's great physics because one is truly probing what is the nature of quantum information, of a quantum system, especially those aspects of quantum systems which are strange and different than classical systems. It's difficult because we are very unfamiliar with quantum systems because when in a complicated environment, the coherence of quantum systems is easily broken and they behave like classical systems. That's why classical thinking is so effective. It's a very good approximation. To get around that is not easy. But the prospects, I believe, for the discovery of new kinds of matter and the creation of new forms of old matter, new phases of superconductors and so on, are very exciting, as is quantum computing in the end. So now let's go down by another factor of 1 billion to the area in which I worked as a scientist early on in my career, the study of the inside of atoms, the nuclear and subnuclear scale. That's a nanometer. And there, of course, we have succeeded in the end of the 20th century to complete one of the great goals of physics, which is to identify the basic constituents of matter and understand how everything else can be built out of these elementary particles and the forces that act on them. So we have identified the basic constituents of matter as quarks, just like all these yellow shirts here. Up and down quarks that make up ordinary nuclei, together with electrons that make up the atom and their neutrino partners, and then 2 other families of quarks and leptons. Most important, we have identified and understood in some detail the forces that act on these elementary particles to create nuclei, to create atoms, molecules, everything we see. So this model, called the Standard Model, it's really better than a model. It's a theory. It's a theory. You can put the equations on a t-shirt. And in principle, the theory has a few parameters. For most things around us, well, only 1 or 2 have to be put in by experimental measurement, but then you can, in principle, solve the equations and calculate just about anything that you can observe or measure. So that's a theory. And this is by far the most successful theory physics has ever had. It includes, of course, as an approximation, the theory we use to understand ordinary matter using quantum mechanics and electromagnetism, and sometimes we need also the nuclear force. Unbelievably successful. In fact, many of my experimental colleagues are frustrated because it's too successful. They want to discover something new that isn't described by our existing theory. I share that a bit, but I'm also very proud of this theory and my small contribution to it. So the standard theory, that's what it should be called. And, again, what's really interesting especially to young scientists, is not what we know already. Well, that's really interesting and fascinating and wonderful. But what don't we know? Where can we discover new things? And one of the important clues that came out of the standard theory, the standard model, we're beginning, is the clue that the forces, all these forces of nature that act at the atomic and nuclear scale, are actually unified, but not visibly at this scale of a nanometer. One of the strong ingredients in developing the standard model was the understanding that the strength of the forces in nature changes with the scale which you're looking at. So famously, asymptotic freedom that was referred to is the phenomena that when quarks are moving close together, they interact weakly.
Can you use this?
But when you pull them apart, you look at that force at larger distance, it becomes stronger, stronger. And that's actually why you can never pull quarks out of the nucleon. But if that's the case, then it was understood perhaps that these different forces like electromagnetism or the nuclear force might be unified, might be the same force, but through mechanisms of what we call symmetry breaking, they don't seem to be at low energies or large distances. If we could probe even shorter distances or higher energy accelerators, we would see that they behave in the same way. And so when the standard model, the standard theory was completed, shortly after, Steven Weinberg, who just passed away a few weeks ago, very sadly, one of the great contributors to the standard model and friends of his, extrapolated the forces described by the standard model using theory to see what would happen if we did experiments at very high energies. And discovered, as is illustrated here, that according to the theory, at very high energies, these forces would converge. So asymptotic freedom tells you that the nuclear force gets weaker at high energy or short distance. Conversely, the electromagnetic force behaves in the opposite way, gets stronger at high energy or shorter distances. So the two come together, but the extrapolation didn't say that they would come together, at 10 to the minus 19 meters or 20. No, it said you have to go to 10 to the minus 35 meters. That's very difficult, unimaginable. But that distance scale where the extrapolation of the standard theory says the forces might be unified turns out to be close to the scale which Max Planck identified back in 1900 when he introduced Planck's constant. It turns out to be up there where the unification scale, that's the scale where gravity becomes strong quantum force. Now, some people are surprised that gravity is so weak because that's the only force they feel. It's the only force they feel because gravity attracts everything, can't be shielded. And the other forces of nature, like the nuclear force or the electromagnetic force, are so strong and they can be shielded, that they create objects like atoms that are neutral and don't exert the force. So that's why if you're lucky, you haven't felt the electromagnetic force. If you do, it could kill you. And even luckier, you haven't felt the nuclear force, because nucleons are made out of objects that carry this colored charge, but they are shielded, confined inside the nucleus, which is neutral. So you only feel these forces if you get very close to the nucleus, and then you get nuclear bombs. But gravity, takes a whole planet to feel the gravitational force. The whole planet is pulling on me. And I can easily deal with it with a little bit of chemical or electromagnetic force by holding this object up, overcoming the whole planet, pulling it down. So gravity is very weak. But the charge of gravity that creates the force is mass or energy. So if you have a lot of mass, or like the planet, or a lot of energy, gravitational force gets big. And at this scale, the unification scale, maybe all the forces unify. That was Einstein's dream. And so many of us have taken this clue and the desire for unification seriously, and have been trying to explore how to unify the forces for the last 30 years or more. And that led us to things like string theory, which is the most successful attempt to do this. It does unify all these kinds of forces that we need in Einstein's theory of gravity and the standard theory of particle physics in a consistent way. And it's very rich, and it has taught us a lot. It's taught us a lot about the possibility of understanding where the standard model comes from. But most importantly, because that's the conceptual hurdle to constructing this unified theory, it's beginning to teach us what is the secret of quantum gravity. Quantum gravity, Quantum gravity is not an easy subject. So 100 years ago, when quantum mechanics came along, Einstein's theory of gravity came along, and ever since then, people have been trying to understand. It's obvious that we have to treat the dynamical space-time, the dynamics of space and time itself, that Einstein explained as the origin of gravity, quantum mechanically. It's inconsistent not to. To have part of the world described by quantum mechanics and part not. But when you try to use standard ways of thinking about it, Einstein's theory, and just push it to the quantum regime, you discover that the fluctuations, the quantum fluctuations in space-time itself become so extreme that you can no longer talk about space and time, and everything breaks down. And it's clear that you need to modify Einstein's theory. People are perfectly willing to do it. Einstein, by the way, was perfectly willing to do it. A few years, he started mucking with his own theory almost immediately after. He constructed it in order to derive quantum mechanics. Didn't succeed. He was on the wrong track. But string theory might be. And one of the most interesting developments is that string theory has started to challenge and offer an alternate point of view of one of our most basic concepts, certainly in physics, the starting point, space and time. For example, early on in string theory, it was realized, although it had been long ago, that maybe there are more than 3 dimensions, 3 spatial dimensions in the real world. but that you don't notice them because some of them are curled up and too small to see except under a good microscope. It's a strange notion, but it's perfectly possible. It's an experimental question. And string theory was discovered theoretically that the theory was only string theory, which is, by the way, a theory that automatically contains gravity. So it turned out that string theory actually dynamically determined everything, including how many dimensions there are. And in some ways of using string theory to create consistent quantum states, you required 6 extra spatial dimensions. And what that means is that each point in space, this point right here, this one, is not really a point. And if I had a very good microscope, I would see that there's structure there. And that structure is pictured in this illustration. Each point has a 6-dimensional manifold, whose structure, the geometry is determined by the analog of Einstein's equations. And you get very beautiful structures. And in those solutions, those consistent theories coming from string theory, the nature of the forces that, say, show up in the standard model and the kind of matter and the parameters that can't be calculated in the standard model are actually determined by the shape and the structure of this beautiful 6-dimensional manifold. Plato would have liked that. Everything is reduced to geometry. We don't know whether this actually is the way to describe our real world. It's not that we can't find solutions like this, that just there are too many, and we don't know which one is correct, if any. String theory has also now given us the tools to probe some of the deep conceptual problems of combining gravity with quantum mechanics, like what happens in a black hole to information. Classically, if you throw a dictionary, which has a lot of information, into a black hole, you've lost that information since nothing can get out. You can't go and look and see what the definition of a word is. You can't communicate with inside a black hole. Quantum mechanically, it's even worse. You can throw entangled pairs, quantum mechanics. 2 parts of a system can be far away spatially, and yet quantum mechanically entangled. And when one pair falls into the black hole, you lose that information, it would appear. And quantum mechanics, you don't lose information. One of the basic principles of the time evolution of quantum mechanical systems is you don't lose information, which is very good because it would really be bad if in the physical world we lost information. Information is precious. Hawking argued that black holes would radiate away eventually by so-called Hawking radiation, and you'd be left with a system that lost information. Well, now we know that isn't the case. And string theory has convinced us of that through what are called dualities, which are remarkable tools of physics, theoretical physics. The ability often to describe a physical system in 2 very different ways, which are both mathematically, one believes, equivalent in the sense that they give the same answers for the same questions, but they're not the same. They're very different dual descriptions. Can't use them at the same time. It's like waves and particles, if you want. And in string theory, this duality is often between open strings, which their ends are attached to some thing we call brains, or closed strings, which describe gravity. The most advanced form of this duality is an equivalence between complicated quantum mechanical systems, which on the one hand describe ordinary matter, even the standard theory, the standard model, in flat space, no gravity. That's one side of the duality, quantum mechanics in M4, which is four-dimensional Minkowski space. And on the other side of the duality, the same physics is described by string theory, or in some regime, gravity, Einstein's gravity, in a higher dimensional space with at least one more spatial dimension. And these two descriptions are equivalent. And that has profound implications for our understanding of quantum gravity of string theory, ordinary quantum mechanical systems, and space-time. For example, the black hole paradox that black holes violate quantum mechanics is refuted, in this case, by producing an ordinary quantum mechanical system with no space and no gravity, and it is clearly information conserving. And in a situation where that's dual to quantum gravity with black holes. In fact, the black hole in this anti-de Sitter space is dual to what is produced at the relativistic high energy collision and at CERN when you collide heavy ions together and you create a state of matter, a quark gluon plasma, which is a hot fireball of quark gluon matter, hot hadronic matter, which lives for a short time and then radiates away and decays. That's somewhat like creating a black hole, which radiates away. And in these special cases, the two are mathematically equivalent. And since one conserves information, so does the other. Now we're using this duality for many, many things to understand better gauge theories, the standard model, because you can apply it to close cousins of the standard model, in particular to QCD, the theory of quarks and gluons. In fact, the origins of string theory came in an attempt to understand the strong interactions. Strong interactions have this chromodynamic field, which creates the force between colored quarks. Here, a quark and an anti-quark. And these lines are the field lines of the force, which, if it wasn't for the strange properties of the QCD vacuum, which is full of fluctuating fields, chromodynamic fields, would go out according to Coulomb's law, and you'd have the strong force would be inverse distance squared, 1 over distance squared, and you could pull quarks out of nucleons and run them in wires and have quark electricity and quark currents and who knows what. But the vacuum is a medium that squeezes these flux lines, wants to get rid of them, squeezes them down to a tube, a so-called flux tube. So this is what the field lines look like between a quark and an anti-quark. And that explains the so-called asymptotic freedom and confinement. This is an actual computer simulation of what happens in QCD. You solve the equations using lattice QCD, massive computers, and you pull the quarks apart, and you see that the field lines, the blue arrows and stuff, is located on this sort of fat string. because of that, the energy it takes to pull the quarks apart to a distance d just continues to increase with distance. So it really takes an infinite amount of energy to pull them truly apart, which is why nobody's ever seen a quark confinement. This is what happens for the proton, made out of 3 quarks, and if you pull them apart, the flux tube is squeezed into this tetrad, and that's why you can't kick quarks out of the nucleon. But you see that these flux tubes are fat strings, and there is no question that there is an alternate way of describing QCD in terms of strings. In very simplified cousins of QCD, this duality can be completed, although most of its structure is not understood yet. QCD is much harder, but that's a long-standing goal, and I have this problem is going to stay around for as long as it takes to solve, which might take 100 years or more. Who knows? It's hard. But there are also applications to ordinary condensed matter systems, which are well approximated by quantum field theories, especially at critical points. Most importantly, to try to answer some truly puzzling aspects of quantum gravity and to suggest how we might really think about space-time. So I'm going to end with this challenge we're getting to. What is space-time? Now, over the years, our understanding of space and time has changed dramatically with Einstein's special theory of relativity, where simultaneity lost its absolute meaning, and with Einstein's general theory of relativity, in which space-time is a dynamical, geometrical manifold, which can be curved and which responds to energy and matter. But now, once again, we're questioning all sorts of aspects of space-time which we took for granted, like, is it really a smooth geometry? Not necessarily in string theory. Is the topology fixed? Can you smoothly change a physical setup from one which has a handle like a donut to one that doesn't, like a sphere? Not in ordinary general relativity, Einsteinian gravity, but in string theory you can. And how many dimensions of space-time are there? Well, it's not even clear what that means in string theory. Sometimes you describe physical phenomena with 10 dimensions, sometimes with 4, or often dual descriptions. So there isn't necessarily a notion of a fixed dimension. So we more and more believe that space-time should be thought of as an emergent concept. There's something deeper. Not atoms of space-time, not at all. These dualities suggest something very different, but that indeed the best way to think about space-time is as an emergent concept. In these dualities, it's not the granular structure of space-time that is being revealed, but rather a dual way of connecting geometry with the quantum information properties of a complicated quantum system. Now that's something nobody imagined before and is being very strongly pursued nowadays to understand black holes, the origin of the universe, et cetera, et cetera, et cetera. But it is really tough to try to imagine what physics will look like if space-time, especially time, is truly an emergent concept. Because physics is all about time, right? You know what the situation is now, the initial condition, You make a prediction in time, that's what we do. But how does time emerge from something else? So I'm finished with a brief discussion of a few other frontiers, and we've had some technical problems and might be running late. I have a very short coda, if you give me 5 minutes. Is that okay? So, some of these questions I've been posing are pretty difficult, especially in the last bit. And it's an interesting question about whether we by physicists, especially theoretical physicists, keep on trying to address these very difficult questions. So I want to briefly remark on 3 possible problems. One is, one way we won't be able to keep going is if we know all the answers. Can we answer these questions and construct a final theory? The other question that some people are worried about is these questions are simply too hard. Maybe we can't answer them. And of course, the other question is always, will we have the will? So briefly, is there a final theory of nature? So I like to construct a geometrical model of knowledge. And what I don't like is what's sometimes called the onion model of knowledge. Knowledge is an onion and you peel it away and you end up at the core. That's the answer, the final theory. I don't like, this is a bad model. It doesn't predict anything and it brings tears to my eyes. So the right model is something totally different, which I emphasized at the beginning. We live in an ocean, a sea of ignorance, in this bubble of knowledge, which is ever expanding. We're pushing it forward. And that model explains something that you're well aware of, namely that as knowledge increases, that's what's inside the bubble, so does ignorance. Ignorance is not the ignorance that we are aware of, the unknown unknowns, is at the boundary of the sphere of knowledge. We're not aware of questions we're too ignorant to ask. So it's only at the boundaries that we're aware. But as we know more and more, the boundary gets bigger, there are more questions. So ignorance also increases. And I'm sure this is something you all have experienced, that the more you learn, the more you realize how much you don't know, and the more questions you have to ask. Knowledge produces great new questions that you couldn't ask unless you had the knowledge. Now, luckily, of course, the volume of a sphere increases faster than the surface of the sphere, at least in ordinary geometry, r cubed compared to r squared. So wisdom, which is sort of the ratio, also increases. So this is a nice model. It explains something we all encounter. The more we know, the more we don't know, yet we're wiser, at least we think so. And so now I can apply this geometrical model to the question of a final theory. So a final theory would be no more ignorance, no more questions. We've answered everything, more or less. And that's happened before. For example, in the exploration of the Earth. This is a Eurocentric map in the medieval times of the known Earth, which is sort of like a sphere, a circle, in this case, disk. And in the map, you can see that there's some idea what might be on the boundary, near to the boundary, but many people thought the Earth was flat. But we know now the Earth isn't flat. or most of us. And we ran out of places to explore. Exploration societies closed down. We have a final map of the Earth up to perhaps, distances of meters. You can get it in Google Maps. That's it, it's over. The final, there are many interesting things to explore about the Earth, but the overall map is known. So is the sea of ignorance compact, like the surface of the Earth? Or is it unbounded and infinite, like a flat Earth would be? If it's compact, then eventually we'll begin to notice that. And in the end, run out of ignorance and have a final theory. Well, I don't know. I'm agnostic. Who knows? How can you decide that? But I don't see, certainly at the moment, any sign of curvature, any horizon. And we would know that. You have to imagine that, in 100 years from now, or 30 years from now, suddenly scientists don't have any good questions to ask anymore. They've answered everything. They say to the funding agencies, okay, we're going to do something else, which will go on forever, like politics, finance. No sign of that. Anyway, actually, if there was a final theory, it wouldn't be the end of physics. There would still be an infinite amount to explore, because even as a reductionist, where you have, final theory from which all in principle would be calculable, that's a very silly thing in practice, and it doesn't truly allow you to explore the hypothetically infinite phenomena and structures that emerge from a reductionist final understanding. More problematic is whether we're smart enough to proceed. We're just speaking animals that have evolved over, compared to our friends, other species, the last 100,000 years. We certainly didn't evolve to construct quantum mechanics or understand the nature of space and time. That wasn't really necessary to survive. Why should we think we're arrogantly smart enough to understand these deep questions? I have been unable to teach my dog quantum mechanics. We understand that it is possible for a species like dogs, which aren't so stupid, to grasp the kinds of things we deal with. What about us? What are our limitations? Well, I think we have an advantage, and that advantage is our primary, what distinguishes us really from all the other species, language, and its amplification, especially mathematics, which is the most advanced form of language. And that has infinite capacity. Chomsky pointed out that a newborn baby, just listening to his parents, can learn a language and utter sentences that have never been uttered before. Mathematics has infinite capabilities, maybe not infinite enough, but pretty infinite. And experimentally, there is no sign that we're faced with questions that can't be answered. So sometimes people who've reached my age say things are getting really tougher, but that's because they're getting old. I don't find that to be the case with young physicists now. You still have these brilliant young minds who manage by their 20s to accumulate enough knowledge of the past to tackle the problems at the frontier and make significant advances. There's no sign that we're running out of capability, but we might, who knows? I think if we do, we would figure out, we'd know how to evolve by coupling to machines or changing our genome, who knows what, but I'm pretty optimistic. The thing that's most pessimistic is whether we and society as a whole will give us the means to continue our scientific exploration, which is indeed getting harder, bigger, more expensive. And here, I don't know, we have to keep trying. One reason we need to communicate the wonder of science, the wonder of exploration, the excitement and the importance and the benefits and the spin-offs, et cetera, job that many of you are doing. Congratulations. But just like, I just hope. And I always like to end with a quote from David Hilbert, the great mathematician, mathematical physicist, who said, we must know, we will know. Thank you.
Hello. Thank you very much, Professor Gross. It was a wonderful talk despite the technical difficulties. We can now take some questions from the public. Okay.
First of all, thank you for your time. And my question is, do you think that the study of physics, the study of forces of nature, will be different with the climate change?
Can you repeat the question, maybe without the face mask? Yeah.
First of all, thank you for your time. And second, my question is, do you think that physics, the study of physics, the study of nature forces will change, will be different with the climate change? And thank you.
Well, I think you're asking, will it affect our understanding of the climate? And well, you know, you saw this year's Nobel Prize, correct? Which was given for the first time, any Nobel Prize, chemistry, physics, anything, to climate scientists. One of whom, the Japanese meteorologist who's now at my old university at Princeton, was a physicist who in the 1960s started analyzing the effect of greenhouse emissions on the climate and predicted the 2-degree rise in temperature. And so the understanding of global warming and of the climate is, of course, based on our understanding of chemistry, physics. It's, you know, it doesn't require truly new fundamental understanding. That's all there and what we know about chemistry and physics. What is required, of course, is the ability to deal with the very complex weather systems that we're faced with. So that's improved slowly over the years, partly because of computers and experiments and measurements. And it's gotten pretty good. And the people who 20 years ago predicted that there would be more and more extreme events, given what we know about chemistry and physics, have been proven, unfortunately, right the last year or two. So I'm very pleased with this prize of this Nobel Prize this year, because it, among the rest, is a way of showing that all of our understanding of this very complicated climate system that we live in is based in the end on fundamental understanding of physics and chemistry.
Professor Daniel Jimenez from Grupo Molecular. I wondered if in your mind, besides any notion of interpretation may arise, if you think there's any mystery to wave function collapse. I would like to know if you think there's any mystery to that topic.
Yeah. So this has to do with the interpretation of quantum mechanics, a problem that has been with us since the invention of quantum mechanics, which is almost 100 years old. So in a few years, 4 or 5 years, we're going to be celebrating 100 years of this, perhaps the biggest revolution in our understanding of nature. And it's not easy. And even the pioneers who created this revolution didn't really accept what they had created. People like Einstein and Schrödinger and others over the years, and there continues to be misunderstanding and lack of understanding and conceptual problems. So my attitude towards that is, I find it all very interesting and look at it carefully, and I don't have time to really explain to you in detail. Most of my time, however, I follow Richard Feynman's dictum, which is shut up and calculate. Somebody would come to him, shut up and calculate, which is what most physicists do most of the time, and it works. So the philosophical understanding of the nature of physical reality, what does the wave function represent, all of that remarkably has no effect on what our understanding of physics at the moment or our ability to make predictions or analyze experiments, and attempts to modify in some way that aspect, the day-to-day working understanding of quantum mechanics, have totally failed. And most of us have no expectation that they. And the other thing is that usually attempts to, people say, this is weird, we should go back to some underlying classical interpretation, some deterministic underpinning, hidden variables. It's not the way things usually happen in physics. Usually, if something has to be modified, like we're now faced with space-time, it gets even weirder. It doesn't get better in the sense of being like it was in the past. It gets even crazier. Yeah, okay, stop there.
Professor Gross, I always was puzzled because by the fact that the Coulomb force can be either attractive or repulsive, whereas at least gravitational forces, and I don't know about the rest, are always attractive. Could it be, does it have anything to do with living in a three-dimensional world?
No.
What's going on?
And it's a very deep feature. There are two kinds of, so actually by now there's a kind of fifth force, but so it's related to the fact that the charge, so gravity and forces like electromagnetism or the strong nuclear force or the weak nuclear force have a lot of similarities. And in fact, that's how in string theory, they're really this. In string theory, one has to do with open strings and one with closed strings. Why that gives the different properties, I won't explain at this point. In particle physics, one is mediated by spin one particles, the photon, which has polarizations, carries angular momentum 1, and same thing with the gluons of the nuclear force, and spin 2 gravitons. Another way of thinking about it is that the charges that give rise to electromagnetism, the nuclear force, are positive and negative. The positive charges repel, positive, negative attract. In gravity, the charge is mass or energy. And there are deep reasons why there are no negative energy particles. There are no negative gravity. But what you're pointing to is a very deep fact of nature, which has many manifestations. And in unified theories, we have a unified understanding of why there is this sort of universal force that's attracted by matter. That's what makes all the difference, of course, for why gravity is so special. Because anything that has energy attracts anything else that has energy. And unlike, a lot of people would like there to be anti-gravity, but anti-gravity would mean objects with negative energy. And once you have negative energy, energy likes to go down to lower levels, decay. It's hard to imagine a consistent universe, but who are we to know? So again, so far, there is no negative energy, no negative mass, and no anti-gravity. Yep.
Yes, thanks for a very nice talk. One interesting part, I think, from what I understand, is for many years there hadn't been any experiments that needed new physics in a way. But now there are these results about the muon gyroscopic rate, the G-2 experiments, that seem to point that something else is needed. Can you comment on what is really what's happening there?
Yeah,
or what you think is happening?
Well, there are there are some observations and many, well, not many, but some observations and experiments that show that new physics is needed. So the the muon magnetic moment is one anomaly. That is now being measured to 1 part in a trillion or close to that. It's something that in the standard model, electromagnetism and QCD can be calculated. Not easy, it's a lot of work to calculate it. The current experimental and theoretical errors are about the same, but there is a discrepancy. It's at the level of 3 standard deviations, or the chance that it be an accident or a fluke is, according to statistics, 1 in 1,000. However, physicists are very experienced with anomalies. They often appear and then go away. And our standards for something really serious is 5 standard deviations. So the experimenters are pushing the experiment currently very hard. And in a year or two, I don't think they'll get to 5, but they could get to 4 sigma. That would be great. In some sense, it would be something that the standard model fails at. And it would definitely mean there's no physics. But it would be very informative. It would teach you something about the scale of the new physics, and you could test various models or against it, see if you could explain it. There are other anomalies that have been showing up at CERN, more 3 sigma-like anomalies. There are these questions about dark matter, which is, a 20 sigma fact. There are neutrino masses. There are so many things that the standard model aren't in the standard model. But G-2 is something the standard model should be able to predict. And if it doesn't, then there's new physics, and you can say what the scale of that new physics is. So it'll be very exciting if it gets firmed up. Also, it does require that the theorists also disagree. There are different big groups of theorists who are calculating, and they're not totally in agreement either. So we'll see.
They tell me there are some questions by people who are online. Let's take a couple of questions from online and then we could come back to the audience here. Okay?
Hello, Luis Alberto Aguilar asks, with regard to detection of gravitational waves, the spatial stretchings detection by LIGO are outstanding small, but at the same time, they seem to be able to pin down the event in the time of fractions of a second. Does this conflict with Heisenberg's uncertainty principle?
So I got the last part. Is there a conflict with quantum mechanics or the uncertainty principle? But I didn't understand what is the conflict, the purported conflict. So I don't, the LIGO requires incredible control over the positions of these mirrors in the interference experiment. They have to worry about thermal fluctuations. They have to worry about trucks 100 miles away going over a bump. They have to worry also about quantum fluctuations. And, but I'm not sure that's the motivation for asking about this conflict. I didn't. Oh. Well, no, the wave, I showed a wave train, it's seconds. It's not the, so I'm not exactly, what they see is a signal, right? And this pulse is maybe 10 seconds, the whole thing is a few seconds. It's not like a particle collision or something like that. It's a wave. And the range they're looking at, that the scale on that was tenths of a second or seconds. So I'm not sure.
Okay, so the second question is, do you think that eventually a superquantum computer loaded with an artificial intelligence will answer all those questions for us? If so, will that be the end of ignorance and human research?
Yeah, I'm not very worried. Computers are pretty dumb at the moment. They're very good at doing certain things, and people speculate about constructing, artificial intelligence has made big advances by not understanding how intelligence works, but just creating these big neural networks that with feedback mechanisms that teach themselves to construct algorithms that we don't understand either. And that works for sorting, pattern recognition. But who knows how far you can push that compared to our few billion years of evolution. So I think, there's no danger of that at the moment. What we clearly are benefiting from with ordinary computers, and even more with quantum computers, will be what we're not good at, which is adding, multiplying, million by million matrices in seconds. That's we don't do that very well, but computers do. What I would like to see is not, and I'm not that worried about AI taking over, but I wouldn't mind having a chip implanted in my head where I could communicate directly with a classical computer, with Mathematica. and be able to think about integrals and see their value, do numerical simulations in my head via this communication with this machine. So nowadays we just do it by tapping with fingers, but if we could get, pretty good signal connection with computers, that could be very useful and expand our ability in ways that I would find much more interesting in trying to construct these neural nets, to try to couple these very efficient adding and multiplying machines to our brain. But I'm not worried that they're going to take over, don't worry.
Okay, let's take another question from the audience.
Thank you, Daniel de la Torre. You talk about the bubble of knowledge and the ocean of ignorance. Even though the bubble of knowledge is growing up in the scientific community, the sea of ignorance is getting bigger in society. And now, in this century, now we have flatlanders and we have anti-vacciners. What is the obligation? So what are how the communication between scientists and community must be in order to make bigger the knowledge bubble in the community?
Well, you probably know the answer. You're trying through your schemes and other people, my schemes. You do what you can. I don't, nobody has an answer to this. This is a problem everywhere in the world, in the most advanced countries, like my country, the top of the scientific pyramid. Still, as more people believe in astrology than just amazing. It's hard for me to understand. You're right that, well, so I was talking about knowledge and ignorance sort of collectively. And indeed, for most of us too, it's a little misleading, that picture, because it's as if all that knowledge is available to all of us, which of course it isn't. But it is somewhere that we can access. We go to a library, or now off the internet, it's all there somewhere. Whereas ignorance isn't, by definition. But why, I don't know why it seems, and maybe it's a question for psychology, there seems to be, most people I meet, or at least come to my lectures, are fascinated by science and really want to understand how it really works and what the evidence is. But there seems to be a large part of a population of any country that finds more attractive these totally nutty ideas. And there's got to be a reason for that beyond just lack of opportunity or lack of knowledge or lack of education. It's unbelievable that the popularity of something like astrology 400 years after Newton. So somebody needs to maybe if we understood that, we could deal more easily with the remaining ignorance among us.
Any other question from the audience? Over there? No? Oh, yeah.
Thank you. Hi, Gerardo. I'm from Ensenada. I'm a science and technology teacher in a secondary school. And my question is sort of one that they already made, respect to the use of computers for building new knowledge. You said previously that building new knowledge has to do with making the right questions. We push the boundaries through that. And do you think that using computers, maybe we could some kind of make that the right questions using like genetic algorithms, artificial intelligence, or quantum computers, or that kind of things?
Yeah, well, computers, you know, follow algorithms. Maybe we do too in some sense, but I don't think anyone's figured out how to build in curiosity to a computer. Computer simply follows orders, which we give it. So certainly at this stage, we're not even, nobody has any idea about how to motivate a computer to explore. However, but there are tools that we can use to explore. And certainly we do. We do. So especially, you know, in theoretical sciences now, computers have become simulation, numerical simulations and computer simulation have become incredibly important, sometimes more important than real experiments. And there we use the best of computers, and it really has revolutionized the way a lot of people do science. And one of the reason Feynman was pushing quantum computers, quantum devices that could do computation, was certainly not to break the NSA protocols and crypto security, but rather to do numerical simulations, quantum simulations of quantum systems. And that is beginning in a big way. That requires, of course, theorists and experimenters who create, you know, real devices in the lab, photonics or cold atoms that can mimic or simulate very difficult quantum systems, which we don't know how to calculate. We don't know what to look for. So that is a new development, which is exploding and very, very useful. But again, we're nowhere near turning this exploration over to computer, which simply follows orders.
Okay, let's take one last question over there.
Hello, good morning. Wonderful talk. It's always refreshing to see a perspective of someone of your degree on the state of physics in the current day. Now, given that here we are mostly educators and students, a couple of scientists, maybe, I'm not entirely sure. Can you tell us a little bit of your thoughts about the needs that technology imposes to us by requiring higher concepts to be developed, such as super advanced physics that nowadays includes topology and weird algebraic structures, quantum computers that now use a lot of quantum stuff, data analysis that involves higher statistics, and all those kind of subjects that require a higher degree of understanding of mathematics, and that we honestly don't see nowadays in high school or college students. So I would like to hear a little bit of your thoughts about this.
So this is not a new problem. You know, Heisenberg, who invented, one of the inventors of quantum mechanics, almost 100 years ago, had never learned about matrices. So he was, PhD in physics from the best university in Germany, which were the best in the world at the time. And he knew a lot of mathematics. I guess mostly analysis, differential equations, PDEs, but not matrices, that kind of algebra, because somehow it was too advanced at the time. Max Born, when he wrote down his uncertainty, his commutation, basis of quantum mechanics, born in Jordan, explained to him, you're talking about matrices, which he didn't know about. It's this, and that is always a problem when at sort of the frontiers, the tools we use are evolving as rapidly as the science itself. Whether they're the experimental tools, accelerators, detectors, microscopes, whatever, always at the frontier, you're having to go beyond, do what other people couldn't do, which often means new tools, mathematical tools, physical tools. And then that filters down to new technology. So there's a lot of talk everywhere about, in all fields, STEM fields, of the need for educate a new working force with higher, more complicated tools. This problem, I think, will be solved. One has to pay attention to it. It's not easy because the teachers have to be educated. That's one of the problems we've had with the computer revolution. So there, luckily, a kid can learn more about computers by himself without the teacher. It's harder to do in some of the fields you described. It's a hard problem, but people are, like you, are aware of it. And first step is, as I said, educating the teachers to incorporate the new knowledge that is required. In the past, I think what continually happens is that you also learn as teachers, educators, scientists, what you can forget. Because you can't, so if you look at the history of the curriculums, they've changed so much over the last 100 years. We used to spend a lot of time doing stuff that nobody does anymore, because you have to do other much more advanced stuff, but you also don't need it. So with the advent of computers, nobody teaches in the United States. Some people complain about it. Nobody teaches people particularly how to write, how to spell. Who needs to know how to spell? The computer can spell for you. So, but some people don't like, I don't like that either. My students not knowing how to spell. But I think that's part of this. You learn how teachers, scientists understand what they need to pass along better, improve their teaching methods, know what they don't need to know, change the curricula, educate the teachers. But this problem, I think, has probably been around forever in human history. And this is just the latest manifestation. We know how to solve it.
Okay, let's take one short last question over there, please.
Hi, Doctor. My name is Ivan Manuel. I'm at a high school called Sitio, BC. And my question is, should we fear about questions that cannot be answered by any meaning?
That's a good question that I'm not sure I can answer, but I often give popular lectures around the world. Sometimes people ask me, okay, physics is good, but can you explain to me why there is something rather than nothing? Okay, that's an interesting question. I mean, I'm sure we all have thought about that from time to time. But then I try to explain that there are scientific questions, and then there are non-scientific questions. And a scientific question is one that can be answered, we expect, by observation, experiment, calculation, theory, modeling. But then there are questions like, why is there something rather than nothing? Or what is the meaning of life? That we all ask, but can't be answered by science, by the scientific method. And I'm not particularly although I do ask, not interested in those questions because they're not going to be answered by science. And I don't know any other way of answering these questions. But there are questions that used to be in one category and now have become scientific, like how does life work? What is life? That has moved from religion, philosophy to molecular biology. We know a lot of the answers to that. That's a scientific question. What is the history of the universe? That's become a scientific question. How did the universe begin? Well, that used to be totally religion, maybe. Now is becoming a scientific question, and maybe we can even answer it. So there's an evolution in the nature of questions. But as a scientist, it's really only going to spend most of my time thinking about questions that can be approachable by the scientific method, and that's proven useful. Some of these other questions have been around forever. No progress seems to be made. Scientific method is the most and perhaps only real tool we have for creating new truths. I'll stick to those.
There will be one just last question from the audience online. I think they already have the question there.
Hello?
Ana Maria?
Yes.
Yes.
I'm here. Thank you. Well, first of all, Professor Gross, thank you very much for a highly stimulating, interesting, informative lecture, and formative also. I think it has given us all lots of food for thought. Thank you very, very much. But there are many questions. We can't give you all because then you will miss your plane. So one of them that is here waiting for a long time is from Eduardo Gomez. What is, in your opinion, the most promising measurement that one can pursue to see effects of quantum gravity or of quantization of gravity?
Yeah, that's a great question. And there's no simple answer. So there are speculative ideas, but usually they imagine extreme luck. For example, not directly quantum gravity, but extra dimensions. So, I talked about there could be extra dimensions. And because the scale of what we think of quantum gravity, of curvature, these most likely, if there are, or that's a good way of describing things, are very small, 10 to the minus 33 centimeters. But that hasn't stopped people from searching for extra dimensions every time you have a new accelerator which probes shorter and shorter distances. And when the LHC started up, one of the first things they did was to look for some of the effects of a world with extra dimensions. And they showed, well, extra dimensions have to be smaller than 10 to the minus 21 centimeters. But there's a long way, and so I don't have any realistic ideas about an observation that could be done to see quantum effects in gravity. It's really hard to imagine. But one always has to push the limits of precision in fundamental physics as far as one can on all fronts, and be open to be surprised. So that's a cop-out. I can't, best I can do.
Okay, thank you very much. Well, I'm sure that we would have, many more questions for Professor Gross, but it's time to close. He has a plane to catch, and I think more important, he has a border to cross. and we are, running a bit late. So, thank you very
Eugenio,
much.
perdón, si podemos también darle la palabra a la doctora Cheto para despedir y luego ya cierras tú la sesión.
Perdón.
Creo que una intervención final de la doctora Cheto ya para despedir la conferencia y cerramos la sesión.
Perfecto, perfecto.
No, bueno, muchas gracias, Eugenio. Muchas gracias, Miguel. Thank you very much, Eugenio, for moderating this session, and Miguel for getting Professor Gross here. It has been fantastic for everybody. I think we all take away something very valuable from this lecture, from this highlights really of both the national conference and the outreach activities in Tijuana. And we hope to see you again. Next time, we hope to meet you in person, of course, and keep well. And thank you again, the audience, for being with us these 2 last hours. Bye-bye. And I'm sorry that not all questions could be answered, but maybe if you don't mind, Professor Gross, we may send them to you. And if you have some time, perhaps on the plane or some other time, you can send us some answers. That would be wonderful.
Sure, I'd be delighted.
Thank you very much.
Thank you, and hope to meet you soon.
Thank you, Ana Maria. Thank you, Professor. Let's thank Professor Gross, please. And un anuncio para los talleristas. Va a haber una oportunidad de tomarse una fotografía con el profesor Gross y también otra con el comité local.